Afternoon. So as Charlie mentioned, I'm a program manager at DARPA, and I run a couple of my programs have an AADL focus, so I'm going to give an overview of those. And I won't go into too deep of a dive because one of the afternoon talks is probably going to go into a little deeper into that program. And I have a 15-minute slot to speak, and I'll probably spend 5 minutes on the programs. And I want to spend a bit of time talking about technology insertion or technology transition. How do we get DoD developers, the defense industrial base, to adapt these tools and techniques and the inherent difficulties in doing so? I'll use my opportunity to speak and the microphone to ramble on about that for a little bit. But first, my two programs that are AADL focused. The first is HACMS, High Assurance Cyber Military Systems. This program started in 2012 by a different program manager. Kathleen Fisher started it. She ran it through the first phase. Then John Launchbury took over and ran it through the second phase. He had the good fortune of being elevated at DARPA to an office director. He hired me to complete it for the third phase. So HACMS, and I tend to think of HACMS as looking at kind of the bottom of the engineering V or implementing software, and maybe up the right side of the V of verification of software. So its focus was, how do we build embedded system software that is cyber hardened? And we broke the problem into 3 levels. The lowest level is operating system software, so software that interacts with the hardware. Then we had the application software, which is specific to that particular platform. And at the top, we had architectural level design. And the way I thought of that was, we have this bag of software parts, all these different components that were separately developed, separately verified. How do we knit those together into a coherent systems that have the right system level properties? And we worked on compositional analysis that was based in AADL, and we're quite successful. The 2 pictures are the transition platforms we worked on. Kathleen Fisher, in her wisdom, set us up to work on unmanned vehicles because they're sexy. And so the truck was an applique for an Army logistics vehicle, and the use case was Army convoys ought to have far fewer drivers than vehicles. And TARDIC, the Army research group, thought, well, the autonomy problem is a lot easier if you just have to follow the vehicle in front of you and do so safely. And the other platform was an unmanned variant of the Little Bird helicopter. So this is a Little Bird's a 2-place helicopter favored by special forces. Boeing is playing around with an unmanned variant of it to do things like medical evac, logistics kind of missions, ISR missions. And the bottom line up front on this is, we started the program, we gave these platforms to pen testers. They were able to subvert them in a small number of hours. And in fact, the helicopter they subverted, it took over the mission computer and could feed nefarious waypoints to the flight control computer, and off it went. And at the end of the program, we gave modified systems back to the pen testers. They have had access to these platforms before. They had all the source code, all the design documents. They've been embedded in the program for 4.5 years. They had exquisite knowledge of the system, and we gave them 6 weeks and said, go. After 6 weeks, they said, we can't find any vulnerabilities, but if we had more people, time, and money, we're sure we could. And that's always the case, I think. So we call that success, and we've been working to transition these techniques to several other DoD programs. But the HACMS program informed the beginning of the CASE program, Cyber Assured Systems Engineering. I mentioned at the beginning of HACMS, we did penetration testing. And what we did was we took the collection of vulnerabilities and we gave those to the developers. And instead of patching those vulnerabilities, they looked at the vulnerabilities and determined, if we re-engineer these systems with these small number of properties, we can remove this entire class of vulnerabilities. So we didn't focus on particular vulnerabilities, we focused on classes of vulnerabilities. So we wanted to make that more repeatable and more automated with the CASE program. So the CASE program is looking at the left half of the engineering V. So how do we raise cyber resiliency to be a first-class designed-in property like all the other non-functional property systems designers deal with, all of the abilities plus safety and performance. And to do so, we have 5 separate technical areas that are kind of the research technical areas. And the first one is, how do we, from a functional model, derive the set of cyber properties that need to be baked into the system? 2 is, once we have these cyber properties, what support can we give to a system designer in terms of automation to modify his model and validate that or verify that these properties are resident in the model, make suggestions to the human designer, help them make trade-offs between resiliency and other properties, verify the model has the right properties, and then help validate that the model and the eventual implementation correspond in a nice way. All the while doing this in a manner that is insensitive to legacy software. And what I mean by insensitive is we don't want to start imposing new requirements on pre-existing software. So part of it is, what architectural patterns can we use that provide resiliency without imposing new requirements on legacy software. But we want to recognize that we're not always going to be able to design around legacy software. At some point, we're going to impose a new requirement in legacy software, and what can we do to modify that software automatically? And we have a performer looking at binaries. So intuitively, new requirements in legacy software ought to be non-functional. We're reusing the software because it has the right function. So the new requirements ought to be some kind of non-functional invariant or data flow or what have you. Can we analyze the binaries to determine, do they have the right properties? And if not, can we modify them to have the right properties, either at design time or with runtime assurance? Another technical area is something I call explainable formal methods. And for a long time, the knock on formal methods has been, you prove a property, that's great. But if you can't prove a property, you don't get a thumbs down, you get often an inconclusive. I can't prove the property. Can you modify your design to make it more amenable to analysis? Engineers hate that. They want to know what's wrong with the design. And if you can't tell them what's wrong, they don't know what to change. So we want to get richer, more actionable feedback out of analysis tools and lift it from the analysis domain up to the design domain so that it's meaningful to the human designer. The last technical area I want to talk about is integration into engineering processes. So we have 2 performers looking at, how do we take this suite of tools, how do we put it into a mature, realistic engineering process in a way that allows the people who are schooled in that process to be efficient. For example, I've talked to a defense contractor who's told me for a program they're on, they use more than 700 software tools in their system design process. So these design processes aren't simple waterfalls or a simple V. They're very complex. There's lots of feedback, and inserting a set of tools into them is not a trivial exercise. I'm going to switch gears a little bit and start talking more about transition. So this is a Collins Aerospace slide. Since they work for me, I feel free in stealing it. One of the things we observed on the CASE program, and it's something that I think I've known before, is a lot of defense contractors claim they do model-based engineering. But if you dig under the covers, they're doing model-based engineering about a ½ an inch thick. And I've had them tell me, well, we really use models to develop pretty pictures to put in our documents. So they use SysML during requirement solicitation to write their requirements document. They use SysML diagrams in their document. And once that's done, they put the models aside and do the real work of engineering. And it's not long before the implementation and the models have nothing to do with each other. It's also the case that one modeling paradigm won't be enough. So SysML does have its place, and I think it's important that SysML is well entrenched in the industry. It's great for thinking about systems at kind of the high level, but once you get down to the embedded computing, you need to have more of what AADL offers you. But in order to make these connections, I think it's important we have the ability to bring design information from a higher level model like SysML into AADL. Now I'm really taking a hard turn talking about transition. So I've worked for a defense contractor for a number of years, as Charlie mentioned. New technologies are often viewed with a fair amount of apprehension as they bring risk into a program. And when I'm talking about a risk from a defense contractor point of view, risk simply means something that's going to make the program spend more money. Opportunity would be something that makes the program spend less money. So they only want to insert new technologies once the risk has been removed. So it's been matured and exercised enough where they can do engineering. When I say engineering, they want the process to be predictable and repeatable. So one mistake that engineers often make is adoption of new technology is done on the merits of the technology. And I'm here to tell you that's not true. It's always a business decision. I talked about risk as being dollars. The decision to insert new technology is a business decision, and we need to come up with data and measures to show the use of model-based engineering is a good business decision. Now, I was at the SEI Research Review last week in Pittsburgh, and there was talk about getting students to use new sets of tools so when they graduate and they move on to industry, they're well versed in these tools. And I think that grounds this kind of a upward transition of technology works for some technologies. So if you have a new software analysis tool and it makes the software analysis more efficient, you can get engineers to adopt it without involving their management because, look, they're doing their job faster, they're spending less money. They don't see that as a risk. But if you have to change the process up front, you have to deal with the program manager. So an industry program manager has one job, and that is to make sure the program stays on cost and on budget. And typically, they use earned value milestones to measure my performance against the cost, my performance against the budget. CPI, SPI, Cost Performance Index, Schedule Performance Index. Again, they want the processes to be repeatable and predictable. So if you introduce model-based engineering, and I think we've heard the term virtual integration in this event a few times, what does virtual integration mean? You're putting more work up front. You're doing the integration work that typically would happen at the end, and you're putting more in the beginning. What does the program manager see? He sees you're spending more dollars at the upfront, and that sets off the sirens. Because the one thing one of the many things a program manager knows, he's going to need management reserve at integration time, because integration time is when the unknowns pop out, and it's a well-known adage in program management. If you don't have management reserve, meaning you don't have a budget of money to deal with risk, you're not managing a program, you're observing a program. So if they spend their money up front doing analysis and virtual integration, they're pretty certain they're going to lose in the back end. So we need a story that'll make the program managers happy. We also need a story to make the executives happy. Here, everything's measured in dollars. So if you want to adopt a new technology, you need to have a good business case. There's two things you can do there is this new technology will allow us to capture more business. So you need to have a a business plan on how this new technology is going to capture more business over some planning period, or reduce cost. And that's typically what analysis tools stand on. We're going to reduce the cost, so of course people are going to like it. You have to understand what an uphill battle that is. So if you're going to reduce cost, you have to overcome what the opportunity cost is of making that investment. So to adopt a new technology like model-based engineering, you have to acquire tools, you have to train your workforce, you have to redesign your process. It is a significant upfront investment. So that's what I have labeled as non-recurring engineering. Then the recurring engineering is, what does it cost to you to do development on each program? And you have to add up the non-recurring and the recurring for each program over some planning period. And a lot of times companies use 5 years. And that has to be much smaller than just executing the programs in the traditional sense. And by much smaller, I mean the return on investment has to be a multiplier of 8 to 10, because they could have spent that NRE developing a new technology that allows them to capture more business, a new sensor, a new capability, etc. So that is the kind of business case we need to come up with for model-based engineering, is how is this a better, in the long run, how is this a better return on investment than the opportunity cost lost for developing new capabilities? I don't mean to seem so glum. I do think that the near future we'll see an overhaul of engineering processes for complex systems. Hopefully people will stop talking about the engineering V. And my new boss, Bill Shirless, who's been at CMU for a long time, wants people not, he gets very upset if I have a V in my charts. Because he thinks that paradigm is obsolete and ought to be put to bed. And I have to agree that the idea we're doing development over here and verification over here is no longer valid. We have to be in a paradigm of verification early and verification often. We're moving into digital engineering. So the DoD has expressed their digital engineering strategy. The Defense Science Board has come out with findings that back up that is the way the defense industry ought to be moving. The technology to do so needs to be matured and enhanced. There needs to be an interlocking mosaic of languages to specify all aspects of the system across the life cycle, from the conception until the end of life. I've talked a lot about the return on investment. I'm gone a little bit over time, so with that, I'll take a couple questions until they kick me off. So the answer is yes, and let me counter that with an anecdote. So I've in discussing with a senior vice president of engineering at a large defense firm and talking about these issues and how model-based engineering analysis will help us bring the errors out of designs early, he said, that's not a valid argument, because you can't tell me the errors that you found when they would have been found otherwise, how much they would have cost to fix otherwise, and if we never find them, they're free. Any other questions?
One quick recall, we do know how long it takes to modernize and upgrade certain fleets, and I'll just leave it at that. So we do have a baseline.
We have stochastic appreciation. We pick them usually with the self-industries. So one of the unfortunate truths about the physical environment from the perspective of the government program manager was that we want to save money, we want to spend money, we just want to spend it all. So sometimes we characterize construction cost savings. We want to, I think, characterize it in terms of crude performance. And because it's all about optimization.
So I agree with what you said in the, if everything's written as a cost plus fixed fee contract, because the cost plus fixed fee, you maximize your profit by spending every last dime. And if you have other contract vehicles, you can optimize for other behaviors. But most defense contracts are cost plus fixed fee. And so the company is, the developer is trying to spend every last dime because that gets them the most profit. Maybe firm fixed price, but that's outside my realm.
Okay, you said errors of omission are essentially free for this vice president. If they're never run into, they're free. But we know from the 737 MAX, which was an error of omission, that's not true. So from a management point of view, just like to say they have to have a risk reason. Why don't they consider having a reserve in terms of errors of omission that they can recover?
So Chris was asking about my funny little anecdote about unfound errors are free, and that was really this person's, I like to think it was tongue-in-cheek a little bit. But the underlying story was some industries, the developers aren't motivated to find the errors because it is a financial risk or a burden to them to have to fix the errors. And if the government finds the errors, the government will pay to have the errors fixed. So again, that goes back to how contracts are written and what have you. But I think most engineers would prefer to develop as error-free of a product as possible. Question in the back? So my sense, and this is one guy's opinion, is that this is the prevalent state of practice in the defense industry is we're going to use SysML to do high-level systems modeling, and once that's done, we'll do the real engineering work. And that way they've checked the box, they can claim to the government customer, yes, indeed, I've done model-based engineering. And we ran into that on the CASE program. So in the CASE program, we have 2 system providers, and one of them started with AADL, the other started with SysML. And they admitted we use SysML to develop pretty pictures for our, and we moved quickly to AADL. Now we are working with them to reverse engineer AADL models from their implementation so that we can do engineering on it and analysis to modify and show that the modified system has important resiliency properties. I don't know if I answered your question, but I got to reiterate that point. Thank you.
Oh, thank you.